Hi, everyone. I'm super happy to be here. So my name is Gaetan Renaudeau. I work at Project September, where we are building a React native application for a fashion app. And we use React Native, we use Redux with GraphQL. Eventually, we will use Relay too. But my talk today is about using OpenGL and WebGL to make effects, GL effects. And I just want to start with this demo. We made this application actually to stress test a bit the library, to see if it works. And actually, we were quite impressed by the performances we reached. Like, the iOS version is running at 60 frames per second, no problem. And we have crazy effects like transition between images. We have transformation over the image here. It's even interactable. You can move the center of that effect. And we even have like effects over text, over views. This actually gets rasterized, so everything is expressed in React. It's a React app. The text is a text component. And we get so the library rasterizes that, inject as a texture, and we can do effects with that. Here's another more real-world example, like a real example, where we have defined so it's like an image effects application. You can add like classical kind of effects, but even more advanced effects like this one. It runs with the same code base, React Native, so iOS and Android, and in the background, we even have a web version of that. Same code base. But let's see GL React. So GL React, basically, you can express using React components a blur, for instance, a blur over video with some negative color. You can compose. We all know how to use React, how to compose components. So we wanted to be able to do that over a video, over an image, over whatever. So composition. And we have actually two libraries. One is for React Native, GL React Native. So it wraps OpenGL. And we have developed also a version for DOM, which is on top of WebGL. And actually, these three libraries are mirroring a bit the React Native, React DOM. So GL React is universal, like React is, and we have the two implementations. So I really love React solves this problem to abstract the DOM. Like DOM is an immutable API, a mutable API, very like imperative style, states everywhere. And thanks to React, we can express our app with like using virtual DOM. We can express at every time the full graph of our application, the full state, in a really functional way. And we have actually tried to solve the same problem on top of OpenGL, which is also like have states everywhere. It's quite low-level API, WebGL. So we've tried to solve that with something we can call virtual GL, so on top of WebGL and OpenGL. But what is OpenGL actually? OpenGL is defined as a pipeline. You have a series of steps that starts from vertices. So you have seen yesterday there was a talk React using in virtual reality. So you have seen how we can use vertices to define 3D shapes, complex shapes, and to make 3D, for instance. So we start with vertices, which are like points that gets piped into a vertex shader, which will position on screen the points. Then we have a step which will actually make triangles out of that. Then it gets rasterized, so we have pixels, real pixels on the screen. And finally, we can color those pixels with a second step called the fragment shader. And finally, you have the blending, which will display things on screen. And actually, in GL React, we wanted to focus on the fragment shader because this part can be hard-coded. And just with fragment shaders, you can do a lot of things. I will show you. So the hard-coded parts will be actually 6 vertices that will be shaped as 2 triangles, just for covering the full surface. So we can color all pixels. But what is a fragment shader, actually? A fragment shader is just a function from point to color. For a given coordinate, x and y, you have to give a color, RGBA. And it's a really interesting paradigm that I like to call functional rendering. It's just a function. Let's see a bit the properties of this paradigm. So I like to say that it's unlimited because it's not limited to primitives like all classical drawing libraries. You don't have like draw rect, draw circles, things like this. Actually, for instance, to draw a circle, you have to think in a totally different way. You have to think I am in this circle, so for the given position, I am in this circle, so you have to use math. Calculate the distance between the center of your circle and your drawing points, and based on that, choose a color. This is how you draw a circle. Just functions. And what's really interesting is it's vectorial by design. It's a function you can run on 4 pixels, but you can run on any resolution you want. It's vectorial. And it's super efficient. This is the key point here. The GPU hardware have GPU units that solve very efficiently, can efficiently call the function on you can imagine it can split your rendering into different parts and run in parallel because GPU units are made for that. It runs in parallel super efficiently, and then back to the surface. And so you can process with GPU millions of pixels at 60 frames per second. It's efficient. Here's the first demo. It's like the hello world of OpenGL, basically. It's just a function from my point x and y, and I will just pass in x and y into the red and green components. Have the blue component are hard-coded, and it will just render that. So it's just like a 2D gradient, right? And how is it actually implemented in a fragment shader? This is the code that runs that. So it's a language called GLsl for OpenGL shading language. And what's a bit surprising here is that you don't actually see it's a function. Functional rendering, it's not a function. Actually, it is. So the input of that function is the varying here. It's a vector 2. So UV is your input, and your output is GLFrag color. You have to set this in the main function that will get called for each point. One important thing also to say is that the x and y coordinates are actually normalized between 0 and 1. So it's quite convenient because everything in this language is use this principle, normalized between 0 and 1. So you can just pass in things, and it works. So let's look at a more real example now. I just want to display an image. So to do that in this paradigm, I have a function called texture2d. I give 2 parameters here. The first parameter is the texture, and the second parameter is the coordinates where you want to look up. So you want to look up in this texture at a given position. And so this will be run on all pixels, right? But this is just a linear mapping. I'm just giving back the same coordinate. So this is why you have just the image. But if you do more interesting stuff, like, for instance, squaring the x and the y, you will have this kind of deformation. So it's like UV time UV. You get the point. I can do anything on x and y and have a transformation out of that. So here I'm just using a bit of trigonometry, sinus and cosinus, and I already have a nice effect. Here's another example I've just written yesterday. It's just adding up 2 gradients together. So I have some built-in functions in this language. For instance, POW and distance. I can use them to combine, to multiply with colors, adding them up, and you can combine effects. If I just add one more gradient. So we can do really interesting stuff with that, in this paradigm, and people are doing crazy stuff on the internet. Can you believe that? It's procedurally generated in a function, with a function. It's like 600 lines of code. One single shader to render this. And you know what? It's actually animated. So it renders like in real time on your computer, like burning a bit your graphic card, but quite impressive. Sorry. So I recommend you to go to these 2 websites. There's a lot of cool stuff out there. All right, let's go back now to GL React. So we have seen that we have uniforms. Uniforms are variables that came from the outside world. So in JavaScript, in our case, we want to be able to change, for instance, the blue. Just changing a bit our previous example, we have the blue that came as a uniform. I'm just passing it into the blue component, so I can have this animation. How can I define that in GL React? Actually, I just take this code, this shader, I put it in this code. So we have a create component function here that takes a function. It's like a render function, so you get props, and you pass in it into a GL node. You can pass in uniforms, and that's it. That's what glues the React world with the GL world. And with that, with my component I've just defined, I can use it like this. And actually, to get a real rendering, you need to put that in a surface, where you give a width and height. And surface can be imported from GL React Native or GL React DOM. So this is where you have our 3 libraries. What you put inside the surface is like universal, and surface is like contextualizing to either the DOM implementation or the native implementation. Okay, let's see how we can support textures. So textures are also uniforms. Here's an example where I define an inverse color component. This is the code that runs that. It's just like 1 minus the color, basically. So I have an inversion of color. I'm using children props, which is special props in React. So I can pass in it inside like as a children. Let's see how I can use that. OK, so there's a bunch of cases. We can use it in many ways. First of all, I can just give an image, URL of an image. I can give a video. So we can do effects over a video. It's only working in the web at the moment. And I can even pass like anything in React Native, like a text, an image, and I will have an effect over that. But the most important part is we can compose things. I can take again my previous example, LGL, passing it inside this, like compose as many times as I want. So this is where it's powerful, I guess, where we can start composing things. And from this composition from this composition idea, we can start building interesting applications like this. So we have a variable blur here. My blur have two inputs, basically. We have the image that we want to blur, and we have a second image which defines where the blur is located. I can also move the blur around, can change the intensity of the blur. So yeah, we can do interesting stuff like this. Can you imagine doing that in CSS or Canvas? I don't think you can. I mean, CSS have filters. CSS have filters, but it's just like a blur filters, but you cannot go further than that. So this is a real world use case I had in my startup. So we wanted to have a text over an image where the image gets blurred just behind the text. So you can easily read the text. So this is where we have implemented like GL React. Let me show you quickly this. Can I switch? OK, it works. OK. OK, so here's the demo, quick demo. So this is like the effects. We don't see it much, but I can change the text here. OK, gets a bit. I forgot the M. We can use different images. And you see that the text is adapting based on the image color. So if I have a dark image, it will be white. Otherwise, it will be black. And we have some blur effects. And we can even put a video behind with the blur effects on top of it. OK. Good. So this is an example. How can we actually, like, I want to use this in my application. What can I write? This is just what you need to write, right? It's like an image title. We have a text. We have an image. So as a user, it's quite easy. OK, I have to contextualize that in a real, like in a surface to have an actual rendering. But that's it on the user side. Let's see how it works actually under the hood. So if you start actually using like React DevTools, you inspect this, and you will see that. So the surface is actually like rendered as a div. And there is two important parts in this div. So this is a container. And we have two pieces. We have contents. And we have the canvas. The canvas, like the WebGL canvas, is actually doing the real rendering. But we also need to, so if you pass in like a title, a text, we actually need to render that in DOM, right? This is why here you have the content. So title will render the text, and the canvas will render the effect. This is the code that runs the full example. So this GL component, the image title component, is split into multiple pieces. Let's see what are there. So first of all, we have the title rendering, which is provided by the title component and another component. In the DOM implementation, it's using a canvas because it's the only way you can get things in WebGL. But for the native implementation, we can just use the text for that. Then we have a second step, which is the blur map. The blur map is the image we've just seen to describe where the blur is located on the image. So we need to pass in the title, do something with it, and we generate this. Then with this blur map, we pass into a third component here, which will do the effect. So blur, a variable blur over the image. And finally, we need a fourth constant here that will give me the average color of the image. So I can based on that, choose the title color, either white or black. And finally, we can just pass in all our variables to the final component and have the rendering. Let's see how this component is implemented. It's itself another GL component. We choose another GL component. So we have two parts. We have a blur. We blur the title. And we have, like with a threshold, we will generate the blur map. And this blur itself is another series of steps. Blur is defined as it's a four-pass blur. This is an efficient way to implement blur. So we split the image on one direction, we split again in another direction, and this is how you can create blurs. So this is how it works under the hood. But because of that, so you see we have a deep nesting, and this blur map gets passed into blurv, which itself is a series of steps, like a multiple pass blur. So this results in a huge tree of components if we unwrap everything. And you see that it's not really optimized. We have 5 times the same things. We have 6 times the same rendering of title. But actually, we can improve that. We can share. We can cache. First of all, we can cache image. We can compute. If it's the same node, we can compute it once. And we can also render once the text. And so the job of GL React is actually to transform our initial user tree into actually a graph where duplicate parts will be factorized. Let's see how it works. So let's just take a simpler example. I have an ad, and I just want to add 2 LOGL together. This is what the graph will looks like. But if I just put that LOGL result, this virtual DOM element, into a variable that I use 2 times, I will actually have the node shared. And how this is working is just working by reference. If 2 virtual DOM is like strict equal, then we can consider the result of that virtual DOM to be the same. It's a nice property of a virtual DOM. So by this technique, we can factorize things, and we can move from this huge tree of 38 nodes, which take 20 milliseconds to render, okay, to this, which is 13 nodes and 4 milliseconds to render. So let's just quickly look at what it does. So we have contents, just to summarize a bit, gets passed into a series of blurs. We have our title blur map that is used to define the variable blur over the image. We also need to have the average color. So we just use 2 blur to squash on X all the pixels, squash again, and then we have only 1 pixel, which is the average color. It's a nice technique. And we can pipe that, and we have the result. OK, let me show you quickly this tool we developed so the tool I've used actually to make the graph image is actually a real inspector tool. Ooh. Oh, OK, it's here. I can just enter the inspector here. I can capture each step to see like what's going on. I can profile, see what the perfs are, like where is my bottleneck in this. I can even, OK, I will toggle back that. I can like profile in real time, like for the rendering. And what's interesting also is you can inspect what are the shaders used by each node. So the blur, one pass of blur is, this is how it's implemented. It duplicates the texture on one direction. And yeah, I guess the most important part is this one, which shows how this graph is actually, like, it's represented in a big object, which is here. And that's just what we need to actually render the scene, to render everything. And this object is what gets passed to the real implementation. So GL React solves the complex problem of turning this virtual DOM, virtual tree into this graph where everything resolved. And at the end, we can like just implement it in the implementations. Okay. So this tool is nice for the DOM version, but for the React Native version, you can just use systrace, which is really important stuff. I really recommend you to use systrace. It allows you to profile things, and we have support for that. So you can see what times each step of our graph takes. So this is just on 5 milliseconds. So you can see where is the bottleneck, everything. OK, let me wrap up a bit. So OpenGL, I like to say it's an ambiguous paradigm. Why I say that is because it's a low-level, imperative-style API, stateful, but also it has like really interesting functional bricks. And the idea here is that we want to hide the imperative parts and just keeping the functional parts. So you can implement universal GL effects. And what's interesting also is that just let people, defining these crazy shader things and exposing them on NPM, and then you can just use them and compose them. Everyone knows how to compose things. And finally, virtual DOM has this nice property that it's referential transparent, and it's nice so we can use that to actually solve our problem. What's funny is that in React DOM or React Native, we didn't have this use case. Like you cannot even share the same DOM elements at the end. But in OpenGL world, it's quite important to not compute 2 times the same thing. So yeah, you can check this out on all these libraries. On NPM, we have a bunch of them, like the classical effects. And yeah, thank you.